Okay, good question. So let me. So excess is only really going to be in one reaction for this exam, and it will be for the hydrazone. So if he gives you excess, he's giving you excess ketone. And this is the reaction where we get like a double substitution. I have the hiccups, please just ignore me. So you would keep this bottom part the way it is, double bond to nitrogen, and then single bond to nitrogen, and then this nitrogen gets the other mole of the. And then any other time he gives you excess, it would be probably like for the acetal reaction. Like he'll just say that there's excess alcohol or whatever. But this is the only thing where something different happens when we have excess. Yeah, the book problems are a lot. There's a lot of stuff in the textbook that Dr. West doesn't care about. Okay. So we're doing some naming. So we have the oxygen side, and then we have the carbonyl side. Which side is considered the parent chain? Oh no! Okay, so the oxygen side comes first in the name, which means that the carbonyl side is the parent. So it's kind of counterintuitive, but it's kind of like, sorry. It's like whatever is named last has the highest importance. So we're saving the best for last. So the red part is going to be what has the OH at the end. So for example, this would be FNO8. And then we would start with whatever is on the blue side, right? So 1, 2, 3. We could say that this would be 2-methyl 1, 2, 3, 4 purple FNO8. So just for practice, that's how we would name that one. So the first thing I would do when going through this question, so we see that it says methyl or ethyl 3-methyl butanoate, right? So I know that the butanoate is going to be on the carbonyl side. So 1, 2, 3, not long enough. 1, 2, not long enough. 1, 2, 3, 4, could be. 1, 2, 3, 4, could be. Okay, so both of these guys have a 1, 2, 3 methyl. So we've gotten rid of 1, 2, 3. We're between 4 and 5. So we know that it starts with ethyl, and that means the oxygen is connected to 2 carbons, which would be which one? 4. Ta-da! So again, to recap, this would be ethyl. This would be 3-methyl butanoate. Any questions? I know this naming can be kind of weird, but are we sort of kind of getting the hang of it? Cool. Number 5, we would keep the 3-methyl butanoate. And let me move this box so you can see. And then on the right side, we have 1, 2, 3 carbons, so it would be propyl 3-methyl butanoate. Yeah, so when you're looking at the parent chain, you start here and you go 1, 2, 3, 4, and this guy's a substituent. Alrighty, so I want to cover the answer, but like, don't look. All right. Look, I didn't ask. Kidding, but also not really. I lied because I don't know what the question mark is supposed to be. Probably an O. Yeah, it's probably an O, so let's. Oh, it can't be an O. It's a triple bond. That's what it is. You're so right. So question mark equals triple bond, right? So let's draw out all the things that are included here. So we have a carboxylic acid. We have water. We have an alcohol. We have a triple bond. And we have NH3. Now, so which one of these guys can we say is absolutely the least acidic? Based off of what we've learned in chapter 17 and then way back in chapters 11 and 12. NH3, because nitrogen is a lot less electronegative than oxygen. So it's going to be better at keeping its hydrogens to itself. So we can go ahead and cross out answer choice C, because it doesn't have NH3 as the last one. Cool. And then the next thing we have to do is, which one of these guys is the most acidic? Carboxylic acid. Okay, one acid is in the name. So that's pretty much always going to be the most acidic, right? And then other than that, it has 2 oxygens. And we know that because of resonance, it's a really, really good proton donor. So we're going to get rid of every answer choice that doesn't have the carboxylic acid as the first place. And we're down to A. Yay! So how do we feel about this one? Pretty good. A lot of the questions on this exam are kind of like this, where you can narrow it down to 1 or 2 answer choices just by knowing like a little bit. So I'm not sure about the exact pKa's, but I think it's like they're super, super close. They're almost the same, but H2O is technically very slightly more acidic. And I think it's just because the negative charge is better stabilized on the alcohol, because the carbons on the carbon chain are going to donate electron density. Okay. So, whatever. Oh, you guys can't even see the answer. Haha, I win. Okay. So we're looking at which one is most reactive to least reactive. And the way this question is worded always bothers me. An addition-elimination reaction. What do we call that? A substitution. And of the nucleophilic acyl substitution reactions, that was a weird way to phrase that. Nucleophilic acyl substitutions. What chapter reactions are those? Ooh, we got 15, 16, and 17. Cool. So this is a great point to review. 15 was electrophilic aromatic substitutions. Those were all about benzene rings. 16 was nucleophilic additions. And then 17 is nucleophilic substitutions. And so the reason it's kind of important that you know these names is, like I said, benzene is all about chapter 15. Ketones and aldehydes are all chapter 16. And then the carboxylic acid derivatives are all chapter 17. So I'm not saying like sit there and like memorize a whole bunch of stuff, like every single thing for 15, 16, 17. I'm just saying it's kind of helpful when you're doing practice problems to know like, okay, this was a 15 reaction, this was a 16 reaction, this was a 17 reaction. And then when you look at the reagents, you can kind of file it, and that helps you figure out like, oh, obviously the answer is not going to be like a benzene ring if this is a chapter 17 reaction. You feel? Okay. Derivatives. Yeah. See, you're the only one who's a real homie. You know what I mean. That's not okay. Just sleeve. There's a hole in my straw and I can't find it, but whatever. Alrighty, so when we're going from most to least reactive for nucleophilic substitutions, we're looking at the different carboxylic acid derivatives, right? Do you guys remember what's the most reactive? Yes, so the acid halides are the most reactive. So we're going to find the answer that starts with acyl chloride and get rid of everything else. So that sucks, that sucks, that sucks. And then we know that amides are the absolute least reactive, but that doesn't super help us in this case because both of those answers have amide. So now it's between esters and anhydrides. Which one is more reactive? The anhydride. Cool. So the answer would be B. Just kidding. Yes, you're right. It would be D. The biggest thing on these exams is like reading the question and reading the answer choices, which as you can see, I don't do. Welcome. Okay, what is the product of this reaction? We're just going to skip that. Okay, cool. Cool. No, just because it wasn't there. Okay, hold on. I'm going to re-download this because apparently half the questions don't exist, which is super. In the meantime, actually, let me not have you sitting here doing nothing. That's boring. Whereas Orgo is so much fun. Okay. Do these guys while I figure the handout out, please. Can you guys see this, or should I make it a little bit bigger? Okay. This is 17. And this is the 17 handout, so you don't have to like rewrite all of them. So I have no idea how much time I've given you so far. How much longer do you guys think you need? Like 2-3 minutes? Is that okay? Okay, cool. So a couple more minutes. Okay, so I see that a lot of people are still writing, but my attention span has just ended. So I can't sit here anymore. Is everyone okay to start going over them now? Okay, cool. So, what is the Rosemary method for chapter 17 questions? Who wants to tell me the 3 steps? Okay, the leaving group. What else? Cross out an H, and then I know you had your hand up. Yes. Okay, cool. So nucleophile or heteroatom, leaving group, and then we cross out the H. Awesome. And then you just draw the product. The sickest benzene ring you've ever seen. Thank you. Ta-da! How do we feel about this? Okay-ish? Yeah, what's up? Oh, just never mind. Okay, so this next one, whenever I do this one, I get a lot of questions that are like, okay, well, how do you know which carboxylic acid will be the nucleophile, which one will be the leaving group, blah, blah, blah. And it doesn't matter because we're going to get the same product either way. So we're going to say this is the leaving group, this is the nucleophile, And we're going to cross out an H. So we end up making O, and we add this carbonyl, and that carbonyl is attached to a benzene. So what functional group did we make? An anhydride. Oops. And I forgot to ask for the first one. What did we make in the first one? A thioester. Yay! Okay, cool. So something spicy. It's not really spicy, but what I told you I was going to tell you. Wow, English is hard today. What I mentioned earlier, I was going to tell you about reaction names. This is one of them. So actually, did Dr. West go over making an anhydride name? Okay, then ignore this one for now. If he goes over it today, we'll go over it. If not, that's fine. Sorry, I got really excited and then I was like, never mind. So who's the leaving group in this reaction? NH2. Who's the nucleophile? O. And then what is the whatever? We cross out the H. Try to make this interactive, but it's the same thing over and over again. Beautiful. Okay, so this is where the new part comes in. We add the O, and then we add 1, 2 carbons. This time I'm not lying to you. This name you do need to know. So what did we end up making? An ester. So the name is pretty straightforward. It's called a Fischer Esterification. And it's not like one specific reaction. It's any reaction where we make an ester from another functional group. So we went from, in this case, an amide to an ester. We could have gone from a carboxylic acid to an ester, from a thioester to an ester, whatever. And we could use pretty much any alcohol and any catalyst. Yep, from any functional group. Hello. Yes, so Fischer esterification is basically making an ester from any carboxylic acid derivative. That's what they're like. All the things in this chapter are called carboxylic acid derivatives. So an anhydride, a thioester, an amide, all those things. Okay, so the next one is fun because we start with an ester, right? And we have our leaving group, our nucleophile, cross out the H, and we get, bam. So what functional group did we make? An ester. So if we go from an ester to an ester, it's not just an esterification. We're going to call it a transesterification. So this is under the category of Fischer esterification. It just gets this little preface because we start with an ester and we end with a different ester. Okie doke. So then this last one, our nucleophile, our leaving group, cross out one of the H's since there's multiple, and we end up with bam, bam, bam. Nitrogen. Nitrogen has 1, 2 carbons and an H. So we went from an ester to a what? Amide. Cool. This one doesn't have a special name. This chapter is weird. Yeah, what's up? Mm-hmm. So they would have to give you NH3 if there's no R group. So then it would be NH2. Yeah. Good question. All right, and then before we go back to the practice problems, I'm just going to show you one more example because I want to tell you the last name. Let me find one. Wow. Ta-da, there we go. And there's no base given here, so I'm going to give you NaOH. And this is page 4, the first reaction of page 4. Alrighty, so in this example, we have our leaving group, our nucleophile, cross out one of the H's. So we went from an ester to a what? A carboxylic acid. Wow, I spelled that really wrong. This is fine. Whatever. It's a day. Just pretend those are words. So when we go from an ester to a carboxylic acid, we're going to call that a saponification. So this is specifically when we go from an ester to a carboxylic acid. And I don't know if this is like the general rule for all chemistry, but Dr. West says you have to have a base catalyst. Yeah, for it to be called a saponification specifically, you need to have a base catalyst, and you go from ester to carb acid. Hello. No, okay, great question. So you could have basically any catalyst and the reaction will happen. It's just only going to be called a saponification if there's base. And it could be any base. He just always uses NaOH. Say that again? If there's no catalyst, still would happen, but not going to be called a saponification. Yes. Yeah. Does anyone still need this before I scroll? Okay. And then so to recap your question, does it matter if it's acid or base you're saying for these two reactions? Nope, doesn't matter. Whatever catalyst it is. Was that also your question? Okay. Okay. What? Yeah. Yeah, exactly. It's just hydrolysis, but we use hydrolysis for a lot of different reactions, so it's not worth knowing specifically. But yes, you're correct. Yes. Yeah. So, okay, here's the thing. He says if you're having a reaction, and let's say the forward reaction is going from a carboxylic acid to an amide, right? You can't go backwards because that's not favorable. But if you try to go from an amide to a carboxylic acid and you have the right catalyst, it's not favorable. It doesn't want to happen. But if you have a strong enough catalyst, it can happen. And so the only reason I'm saying that and making that distinction is because you have to know that specifically the one reaction that absolutely cannot happen by nucleophilic substitution is anything turning into an acid halide. Because you have to know that you have to use one of these reactants. Does that sort of kind of answer your question? Okay. Could happen, yeah. No, it's more just like if he gives you like a reaction, whichever way, if it's going from more to less stable or less to more stable, you should be able to know what the product is. It's not a trick there, but he'll ask you a concept question that's like, oh, is it favorable, or what's the most favorable like change? And then you have to pick the one that goes from more reactive to less reactive. You're welcome. All right. Any more questions? Yes. Exactly, because we specifically have to use one of these guys, and all of these guys have to have an OH to turn into a halogen. Good question. All right, so let me open up. Did you have a hand up or were you just stretching? Okay, cool. I feel so bad. I've interrupted 3 yawns today. Okay, so let me send myself the practice problems so you can see them. I pressed airdrop and it went, are you sure you want to print this? And I was like, no. I didn't say print. Great, you know, spiky. All right, so we did this one. We did these ones. We didn't do this one. Okay, cool. Yes, okay. So, what is this starting material? Lactone. Cool. And specifically, what kind of lactone? Yes. So we have alpha, beta, gamma. And this is a gamma lactone. So when we're doing the lactone reactions, we're breaking it apart. We're still gonna say, okay, this is our leaving group. This is our nucleophile. Cross out the H. But the big difference here, you guys have to remember, we're not completely getting rid of the O. That's the leaving group. We're just opening up the chain and adding it to one side. So I'll show you 2 ways to do this reaction. So first we count. We go 1, 2, 3, 4. So I know it's a 4 carbon chain. 1, 2, 3, 4. And I know that on carbon 4, I have an O, right? And I know that on the carbonyl, I'm going to add the nucleophile. So we get OCH3. And what does the O on carbon 4 turn into? OH, or an alcohol. Perfect. So then you can just match up whichever answer fits. And that would be which one? Number 2. Cool. The other way to do it, yes, what's up? Yep, it's just a leaving group. It opened up. Good question. So the other way that I would do this is I would just look at this and say, okay, lactone with a nucleophile, we know we're going to break it open, right? And this is where the chapter 15 versus 16 versus 17 comes into play, right? Because I know if I see a lactone, that's chapter 17. So chapter 17 reactions are substitutions. So purely based on that, I can get rid of this answer choice because that's an addition reaction. I can also get rid of this guy because where the heck did I get another carbonyl from? Trash. And then I can get rid of this because why did I keep a carboxylic acid on one side and then add an ether on the other side, right? That makes no sense. And now we're stuck between 2 and 3. And how I think of it is there's no way to get a carbon on that oxygen at the end. We haven't seen any reaction that does that, so we get rid of it. And 2 is the only one that makes sense. Yes. Yes. So let me erase some of this gunk. So the only bond we can ever really break is specifically the carbon-oxygen bond. So that's the one we're going to break here. Yeah, so we're essentially going to replace it. So we're going to break this open and kind of open it up that way, and then we add this in its place. The thing that they did to kind of trick you is that they flipped it around from the way that you would have drawn it or I would have drawn it. But does that kind of make sense? Okay, cool. So any questions on this one? Do we feel okay about it? Okay, cool. All right. This is a good question. So I'm going to let you guys look at this for a minute, and then we'll do it together. But I do want to give you a chance to look at all of these and think about it. And like you can go ahead and highlight leaving group nucleophile. Okay, does anyone want another minute? Or are we okay to go over it? Everyone's like, I didn't even want to start working on it in the first place. That's fair. Okay, so so it's kind of a good thing that we don't use the board anymore. Not really, but also because I accidentally threw markers at people, and like dropped them. So at one point, what? Accidentally, I would never purposely hit anyone. Duh. But no, there was at some point a girl who sat in the back and like tallied every time I dropped my marker. And at the end of the semester, she was like, "You dropped your marker 74 times." I was like, "Cool, dude. You're so cool." It was really funny though, actually. All right. Anyway. No, it was a running joke. And we had like paper attendance, and at the end of the week, she would put like the number at the end, and I was like, I get it. Okay. So this first one, is this a chapter 17 reaction? No, why not? That's okay if you don't know why not. Okay, that's a good observation. The plus is on the Na, the O is on the oxygen. So with that, what do we think? Okay, kind of, sort of, yes. And it is a substitution reaction, but so are chapter 17. But I think I know like what you're saying. So this isn't going to be like the nucleophile is this guy and he attacks this and we replace whatever. Instead, this oxygen is the nucleophile. The Br is the leaving group. And this is going to be almost like an orgo-1 substitution reaction, right? So we're going to attack here, pick off the leaving group, and the NABR go off and do whatever. So we end up with O, CH2, CH3. So that one does make an ester, yay. We've been doing a nucleophilic acyl substitution. This is like a regular substitution. The reason they're different is because in a nucleophilic acyl substitution, that implies that we have the carbonyl and then we have our nucleophile. The nucleophile can't be the carbonyl. Cool. This is from like orgo-1. like SN1, SN2 kind of thing. I think this would be an SN2. Yeah. No. Fun fact, when I was studying for the MCAT and I saw SN1, SN2, I was like, are you kidding me? It barely comes up though, so it's great. Anyways, so for B, does anyone see a problem? OH, okay, cool. So we have OH, we have the minus. Why is that a problem? It's not a good leaving group, true. What else does that O on an alcohol tend to want to be? A lot of people are like, it wants to be a nucleophile, right? In all of chapter 17, the O has to be the nucleophile, right? So now we have the O minus and the OH that are both nucleophilic. Can you have a nucleophile react to the nucleophile? No. So we see that there's kind of a problem with B because both of those guys want to be a nucleophile. So we're going to put B on hold, right? C. What chapter? What kind of question is this? Yes, it's an esterification. Cool. So this is actually a chapter 17 question, and we know the difference between A and C is that A has the O on the carbonyl as the nucleophile, whereas in C, this guy is the nucleophile, this guy is the leaving group. So what makes these reactions so different and kind of opposite is that in A, that O has a negative charge. In C, that O has a hydrogen. So that negative charge makes a huge, huge difference. So in this case, we end up with the same exact answer, but because this one attacks here and kicks off the leaving group. Do we kind of sort of see that? Okay. Some people look unhappy about it. Yes. I mean, it kind of could, but it doesn't really want an H to begin with. If that makes, or I kind of see what you mean, but it wouldn't be the best reaction. People don't look happy about it. That's fine. Let's just do D and E and then we'll go back to B. So in D, what are we starting with? An anhydride, and this guy can act like the leaving group. This is a nucleophile. So we get, again, an ester. It looks slightly different, but it's still an ester. And then for E, what is the starting material? Like, what's the functional group? An acyl chloride or an acid chloride. And then this right here is the nucleophile. So we get an ester. It looks slightly different again, but it's still an ester. Okay. So A, C, D, and E. A is a little bit different than the other answer choices because it is a different type of mechanism. But the big thing here is that in answer choice B, the OH is a terrible leaving group. And we have two nucleophilic species that don't really want to interact with one another. And if they did react, it would be like a way different reaction mechanism and it would be super unstable. So for that reason, B is not really going to react to form an ester. Yes. So we could, if we had an acid, but theoretically an acid would protonate both of them. So it would still be like a weird reaction, if that makes sense. It could happen, but it's really unfavorable. Unfavorable. And wink, wink, nudge, nudge, he does tend to have something similar to this on the exam. And this usually is like the catch or whatever. Yes. Yeah, because we have a negative on the carbonyl, and then we have an OH, which is also nucleophilic. Okay. So this next one, again, this question isn't hard. It's just phrased in a really weird way. So gamma and delta hydroxy acids can be esterified intramolecularly, blah, blah, blah. Like what does this mean, right? So hydroxy acids, all you have to know is that this is a carboxylic acid that has an OH somewhere, right? So it's saying that we have a carbon chain that has both a carbonyl and an OH. And we also see that it says esterified intramolecularly. So what is the only intramolecular reaction we've learned about in chapter 17? Lactones and lactams. So we can get rid of anhydrides, whatever that is. Cyclic ketones, wrong. So we're stuck between lactones and lactams. How do we know to pick lactone and not lactam? Exactly. So a lactam is a cyclic. That's lactone. So yeah, a lactone is a cyclic ester. A lactam is a cyclic amide. And we can say A is for amide. O is for the O in an ester. O in an ester. So if this said a delta or gamma amino acid, then it could have been a lactam. But if it says hydroxy acid and it also says esterified, we know that it's lactone. Any questions with this one? Yes. Yes. So if this was an amino and it didn't say esterified, then it would be a lactam reaction. You're very welcome. Okay, so to wrap up the session, someone tell me what a saponification is. Yes, specifically ester to carboxylic acid. What kind of catalyst? Base catalyst. Cool. So what's the difference between a regular esterification and a transesterification? Yes, so regular esterification is anything to an ester. A transesterification is from one ester to a different ester. Awesome. I will see you guys later.